We present SCADE, a novel technique for NeRF reconstruction under sparse unconstrained views for in-the-wild indoor scenes by leveraging on ambiguity-aware depth estimates. When estimating depth from a single image, there can be multiple, equally valid depth estimates. These arise from inherent ambiguities such as albedo versus shading, scale, or non-opaque surfaces. We retain these ambiguities at the stage of monocular depth estimation by representing depth as a distribution represented with samples, using CIMLE. The ambiguities are resolved by fusing together information between different views, which is done using a NeRF combined with our proposed loss function. This can be viewed as a probabilistic generalization of space carving. Results on different datasets show that our approach enables better photometric reconstruction with better recovery of non-opaque surfaces and crisper object geometries. Now let's dive into the details. The main idea is to leverage depth as a prior in order to constrain NeRF optimization under the sparse view regime. The benefits of depth compared to other priors are twofold. First, it is category agnostic, and second, it generalizes to in-the-wild scenes. The question then becomes, how do you fuse the depth predictions from multiple views? We draw inspiration from the classical space carving technique to tackle this problem. In classical space carving, the goal is to find the coherent geometry that satisfies the observations from the different views by carving out empty space. This works great assuming the availability of ground truth depth. But we know that monocular depth is inherently ambiguous, such as albedo versus shading and scales. Hence, we represent depth as a distribution, which can be multimodal and retain the inherent ambiguities at the stage of monocular depth estimation. Thus, in contrast to classical space carving that uses point estimates without modeling uncertainties, we propose a loss function that is a probabilistic analog of the classical space carving, where uncertainties are modeled and ambiguities are only resolved once information is fused together from multiple views. Our approach is mode-seeking and finds the consistent valid mode across multiple views, thus preventing the output from falling into an invalid mean. First, we go through our ambiguity-aware prior that represents depth as a distribution to handle the ambiguities. This distribution can be multimodal, hence we represent ambiguities as samples via conditional implicit maximum likelihood estimation, or CIMLE, to capture variable depth modes. Here is our network architecture. It is a simple combination of a state-of-the-art monocular depth estimation network, LERES, with CIMLE that is implemented by adding add-in layers to the encoder. This allows us to output a distribution of possible depths from a single image, represented as a set of samples. We find that our ambiguity-aware prior is able to capture the different ambiguities, such as albedo versus shading, as shown in the door frame, different scales of concavity of the sofa seat, as well as multimodality in the outputs of non-opaque surfaces. Now, why does it work? Here we have some training image examples from the taxonomy dataset used to train our prior. We observe that different training images label depth differently. For example, shooting through the glass, on the glass, or a mixture of both. This allows our prior to learn multimodal outputs. We also observe that our trained prior is able to capture variable depth modes on reflective surfaces that typical monocular depth estimation networks struggle on. Now we present SCADE. When only given one input view and its samples from our ambiguity-aware prior, it is ambiguous. However, when given a sparse set of views, we are able to resolve the ambiguities by fusing information from the multiple views. To do so, we draw inspiration from the classical space carving. Here is an illustrative example to provide the intuition. For every view, illustrated by the green and yellow cameras, we have multiple depth hypotheses from our ambiguity-aware prior. For simplicity, let's assume there are 2 hypotheses per camera. Space carving eliminates inconsistent hypotheses. For example, green hypothesis 2 is not consistent with both yellow hypotheses, because if it were consistent, everything in front of the green camera cone should be empty. Thus in SCADE, we distill the consistent hypotheses for each view into a global 3D geometry, represented with a NeRF. To achieve this, we introduce our novel space carving loss functions on the two distributions, our ambiguity-aware prior and the ray termination distance of NeRF, that is differentiable and sample-based. Let's go over the space carving loss function. It is given as follows. It drives the learned depth distribution from the NeRF to be consistent with some depth hypotheses in every view. Our resulting loss function is mode-seeking. Moreover, as opposed to existing works which supervise in 2D moments, we supervise at individual samples along each ray in 3D. We show results on in-the-wild captured scenes. Notice that we achieve better photometric reconstruction, especially on non-opaque surfaces such as glass, where our output is less blurry and enables the recovery of objects behind the glass wall. We also show results on SCANet, where we see that we are able to recover crisper shapes as shown by the black office chair. Finally, here is a scene from the Tanks and Temples dataset, where we see our output results in cleaner reconstruction as our space carving loss supervises in 3D and is able to clear up dust in front of object surfaces. Quantitative results also reflect the advantages of SCADE. Finally, we also show rendered depth maps and TSDF fusion results. Thank you.